Hey, welcome back to Linear Algebra. We're going to start our work in section 2.4, talking about invertible linear maps. So the outline is written here for you. I want to start by recalling what I mean by an invertible function. That's a Math 240 concept that you saw there. And then I want to show in particular in the case of a linear map, if you have an invertible linear map, it itself is linear. That's theorem 2.17. And then we're going to talk a little bit about what we mean by invertible matrices. The conversations in our course for the last couple of lectures have been about the relationship between invertible maps and matrices, so you're probably not surprised that we're going to look at some theorem that says that a linear map is invertible if and only if the matrix that represents it in any pair of ordered bases is also invertible. So that's theorem 2.18. Okay, so those are the major results that we'll cover in this section, at least part of this section anyway. Let's get going here. So first of all, what do we mean by an invertible function? I'm going to just continue to use our function notation like these things are vector spaces, but in this definition, v and w just have to be sets. T can be any function, but a function between two sets, v and w, is called invertible. If there's a function, and I'm building in its notation, I pronounce that T inverse. If there's a function that goes, quote unquote, the other way, so it's a function whose domain is the codomain of t, and its codomain is the domain of t. So it reverses the arrow in the function direction. And then what does that function have to do? It has to satisfy, I like to think of it as two properties. That first of all, if you take any w in w and you apply t inverse to it, and then you apply t to that, you have to get w back. And the other way around, if you take any v in v and you apply t to it and then take t inverse of that, you have to get v back. In terms of function composition, alternatively, I could have just said that a function t is invertible if there's this other function t inverse from w to v, such that the composition of t and t inverse is the identity on w, and the composition of t inverse and t is the identity on v. Okay? You recall from Math 240 that a function is invertible if and only if it's bijective, right? So it has to be 1-to-1 and onto. That's when you can define an inverse. And then using a little bit of our previous theory, in the case of a linear map, then T would be invertible if and only if its rank was equal to the dimension of the domain, right? Because the rank nullity theorem, among other things, says that this rank is equal to the dimension of the domain if and only if the dimension of the kernel is 0, the dimension of the null space is 0, which means it's 1-to-1. Or if you prefer, because all of that is kind of symmetric, a linear function is invertible if and only if its nullity, the dimension of its null space, is 0. Because the rank nullity theorem says if the dimension of the null space is 0, then the dimension of the rank has to be the dimension of V. All right, so those are kind of conditions that are special for linear maps when they're invertible. So you can take any one of those to be the definition because they're all equivalences. A couple of other things I want to remind you of that these conditions up here, they kind of simultaneously, well, they one thing you can infer from them is that if T is invertible, so is T inverse, and the inverse of T inverse is T. That actually requires kind of one more little comment about inverses being unique, but it's true. The inverse of the inverse of T is T. And then here I didn't write it, but if T1 and T2 are both invertible, then their composition is invertible. And the inverse of the composition is the composition of the inverses, but you have to switch the order, right? So T1, T2 inverse is T2 inverse composed with T1 inverse. Those are nice little exercises that you should assign yourself. All right. So let's start looking at our first major result here. I've got the proof written out, and as usual in these videos, what I'll do is just kind of narrate it, talking as fast as I can to keep the video short. You pause a lot trying to soak the stuff in. All right, so hopefully you're watching these things and doing exactly that. So what does the theorem say? All right, so it's about the first bullet point in our objective. If you take a linear map T from V to W, and suppose that it's invertible, then its inverse is also invertible. Or sorry, its inverse is also linear. Of course, its inverse is invertible, but its inverse is also linear. Okay, so that's the kind of upshot of it, is that if your function is linear, its inverse is linear when it's invertible. So how to prove that? Well, a linear proof, T inverse is a map from W to V. So a linearity proof should start by choose two elements of the domain and a scalar. right? I need to show that property that sums go to sums and scalars go to scalars, and I'm going to do it in the all rolled up into one version. But this is how a linearity proof starts generically. Pick two elements of the domain, pick a scalar, okay? Okay, so once I pick these two elements, W1 and W2, well, because T is invertible, there's unique, actually, vectors V at 1 and V2 back in V that map to these W's. All right, so if you want me to unpack that a little bit, why do these V's exist? They exist because T is onto. Why are they unique? Because T is 1 to 1. T is invertible, so it's both of those things. And here I'm just rewriting. If T of V1 is W1, well, then T inverse of W1 is V1, and so on. I could have just named V1 and V2 by those green highlighted equations as well, whatever you like. Okay, and so now what am I going to do? I'm going to check the linearity condition. So I'm plugging in this linear combination, C times W1 plus W2, into T inverse. And all I'm doing is saying, well, W1 was T of V1, and W2 was T of V2. T is a linear map, right? So C, T of V1 plus T of V2, I can write that as T T of C of V1, V2. Right? So if you want me to kind of highlight my proof here a little bit, that's by the linearity of T, that equality, all right? But now I'm just using the invertibility. T inverse composed with T is the identity, right? When you take T inverse of T of something, you get the something. And then the last thing I'm doing is just rewriting in what V1 and V2 are in terms of T inverse and W. So that's it. So at the end of the day, what did we do? If I kind of go back and summarize my proof, for an arbitrary pair of vectors in W and an arbitrary scalar C, T inverse of this linear combination is the linear combination of the T inverses. T inverse is linear. Nice. Second theorem, I don't have a number for it. It's not numbered in the book. I actually think the book calls it a lemma. So this is in this section 2.4. But I'm going to call it a theorem. I think it's an important enough result to be called a theorem. But what does it say? It says if you take, let's suppose we have an invertible map between two vector spaces. So it's kind of a compound statement. So let me kind of highlight them. So the first statement is that V is finite dimensional if and only if W is. Okay, so if you have an invertible map and the domain is finite dimensional, then so is the codomain, and vice versa. And in fact, we can even say more. In that case, those dimensions are going to be the same. Okay, so if you have an invertible map between two finite dimension or between two vector spaces, then the vector spaces are either both finite dimensional or they're both infinite dimensional. And in the finite dimensional case, the dimensions are going to be equal. Okay, so how do we prove this? I like this proof. It kind of illustrates a lot of our ideas. So suppose that we have some linear map T and it's invertible. That's just taking our hypothesis. And then to give us some notation, let's suppose that V is finite dimensional. Let's say beta is this ordered basis for it, V1 to Vn. Okay, so in particular here, I'm assuming that V is finite dimensional and its dimension is n. All right, so if we take the image of those basis vectors, right, by a previous theorem, it's theorem 2.2, I looked it up for you, that set T of beta spans the range. But T is an invertible map, so it's onto, so the range is equal to W. So T of beta spans W. Okay, T of beta is a finite set, so first of all there, W is finite dimensional. It's got a finite spanning set. And then moreover, T of beta cannot have any more elements than beta does, right? Because T might send distinct elements in beta to the same thing, but it certainly can't make more. So T of beta has no more elements than beta does. T of beta contains a basis. It's a spanning set. Every spanning set contains a basis. That's theorem 1.9. I looked it up for you. So I know that the basis for W, not only is W finite dimensional, we've already deduced it, but its basis couldn't have any more than the number of elements that beta does. That is, the dimension of W is less than or equal to the dimension of V. Okay? But this is the cool part of this argument. It's what I like about it. So everywhere I was talking about T and beta, but you could just flip the argument. Flip the argument, but apply it to T inverse. Take a basis for W called gamma and go through exactly the same steps. And that same argument will show that if W is finite dimensional, then so is V, and you get the same, or the reverse inequality. All right? So there you go. If one of them is finite dimensional, then so is the other, and vice versa. And we can argue that the dimensions satisfy these two inequalities, and hence they're equal. Nice. Cool. All right, I'm assuming that you've seen this definition rather before. What do I mean by an invertible matrix? So if I take a square matrix, A has to be square. It's called invertible if there's some square matrix of the same size whose product with A in either order is the identity matrix, right? That's what I mean by a matrix being invertible. And if there's a matrix B that satisfies that equation up there, it's unique. Because if you had another matrix C that also satisfies that same equation, A times C is C times A is the identity matrix, well, then you could write C as itself times the identity matrix, but the identity matrix is A times B. Matrix multiplication is associative, but C times A is also the identity matrix. And so we are able to deduce that A is equal to B. Okay? So because it's unique, I'm going to just use this notation. I'm just going to write A inverse. I'll call it the inverse of A. You pronounce this thing A inverse. And what is its property? A inverse is a square matrix, if it exists, that when you multiply it by A in either order, you get the n by n identity matrix. We'll postpone the topic of how to compute A inverse given A till chapter 3. All right, so moving along here, this is our last result of this short video lecture. It's called Theorem 2.18, and it's the relationship between an invertible linear map and the matrix of it in any pair of ordered bases. Okay, these theorem statements look long, but most of it is just notational setup. So got a couple of vector spaces, the usual names. They're finite dimensional. Usual names for ordered bases, beta and gamma. Okay, using the same kind of notation. V has a basis called Vi, as I goes from 1 to n. W has a basis called Wi, as I goes from 1 to m. Nice. All right, so the statement is that a linear map from V to W is invertible if and only if the matrix of it in those ordered bases is invertible. And then as a bonus, we even get something more. The matrix of the inverse map, note the order, T inverse goes from W to V, so I'm saying it's the matrix in the gamma beta basis. It's just the inverse of the matrix of T in the beta gamma basis. Okay, so if I said this out loud, instead of symbols, it's saying that a linear map is invertible if and only if its matrix is invertible. And the matrix of the inverse is the inverse of the matrix. Okay, very nice fact. So this compatibility between linear maps and matrices continues to be sort of flawless. Yeah, the two notions so far seem completely interchangeable. That's the picture we're trying to paint. All right, so hopefully you wrote that down. You can pause the video and go back. Let me just walk you through the proof here. So it's an if and only if proof. So let's pick a direction. I'm going to, in particular, suppose that my map T is invertible. I'm going to use a lot of the notation from the statement of the proof. Okay. So by our lemma above, if T is invertible, then V and W have the same notation. Okay, that's by the lemma. They have the same dimension. So our two numbers, n and m, are actually equal. And then I did some searching in the book. I found a couple of theorems that I'm using there, 212D and 211. I'll try to tell you where I'm using them. But I'm just going to start on the left-hand side of this equation. If I look at the identity matrix is the matrix of the identity map in any basis. Okay, that's 212D, I believe. So let me just write there, 212D says that. Right, but the identity map 1 sub v, that is the composition of T inverse and T, because T is invertible and T inverse is its inverse. So I can just swap 1 sub v for that composition. And then the matrix in a basis beta of a composition of two linear maps is the product of the matrices. That's the 211. So theorem 211 says that the product of those matrices is the matrix of the composition, right? And you have to have the bases right. So T inverse is in the gamma beta basis, T is in the beta gamma basis. The second line, I'm just reversing the roles. The identity matrix is also the matrix of the identity on W in the gamma basis. The identity on W is the composition of T and T inverse in that order. And then use theorem 211 again. Okay? So what do those two equations tell me? It tells me if I look at these two matrices, T inverse in gamma beta and T in beta gamma, their products in either order are the identity matrix. So that precisely shows that this matrix is invertible. And by uniqueness of inverses, it says that its inverse is the matrix that we're multiplying by there. Okay, so that's half our theorem. Pause the video and digest it. I'm just going to plow on here. To go the other way, now I'm going to suppose, I'm going to give it a short name A, that the matrix of T in the beta gamma basis is invertible. So remember what that means. That means there's some other square matrix whose products with A in both orders is the identity matrix. All right, my goal is to show that T is invertible, so I'm just going to produce its inverse. Let me define an operator U from W to V. Remember, I can define an operator by specifying its values on a basis, so that's what I'm going to do. For every I, for every j, excuse me, every j from 1 to n, I'm just going to define U of Wj to be this linear combination of the V's. And what are those Bij's? Well, they're the elements that are the entries of the matrix B. So I'm consistently using that same kind of notation. So I have this matrix B, I have its entries. So for a fixed J, I take the entries in the ith row of B, for a fixed J, I take the entries in the jth column of B, and I multiply them one by the corresponding vector VI, and I add from I from 1 to n. And if I do that, then by definition, stop the video and make sure this makes sense, but it literally is by definition, the matrix of U in the gamma beta basis is B. It's the matrix B. Okay, now I'm going to just bust out these theorems again. If I look at the composition of U and T in the beta basis, that makes sense because U composed with T is a map from V to V. Well, by theorem 211, that's the product of these two matrices, right? But the matrix on the left, U in gamma beta, we called that B, and the matrix on the right is called A, and those two matrices are inverses of each other. So I get the identity matrix. And the identity matrix is the matrix of the identity map in the beta basis. All right, so now what I'm going to do is focus on the extremes in this equation. It's telling me that the matrix of the operator UT in the beta basis is the same as the matrix of the identity map in the beta basis. But we have a previous result. You can find it. It cites a corollary, but I went and looked. It's a remark on the bottom of page 80 that says when two operators, two linear transformations have the same matrix in a basis, then they have to be equal. All right, so that remark implies that UT has to be the identity map on V. Good. Go back and repeat the entire argument. Flip it around. Flip the argument around, and you can show that the composition in the order TU is also the identity on W. So by definition, U is T inverse, so T is an invertible map. And moreover, this matrix B, which we defined above to be the this is T inverse. Remember, U is T inverse. So its matrix in the gamma beta basis is the inverse of the matrix A, which is the inverse of the matrix of T in the beta gamma basis. All right, so that is the end of theorem 2.18, and that's what I wanted to accomplish in this video. So thanks for listening.